So to wrap up this section on steel flexural members, what have we learned? Well, we learned that local buckling is really not an issue for most beams for A992 steel, but you got to be careful when you get into situations where you're using a built-up section or in those few wide flange sections we talked about where there might be a slight reduction in moment capacity. We learned that effective bracing must be provided at the ends, that is at the supports, to restrain rotation about the longitudinal axis. And we talked about what constitutes an unbraced length, what constitutes a brace point, and we, most importantly, learned about C sub B and the fact that if you take the trouble to understand the C sub B equations and use them, you often realize some significant savings in your non-composite beam design. Okay, that wraps up this first section. Let me open it up to any questions anybody had that came to mind about that. Yes, sir, over here. I'll repeat the question. Go ahead. Yes. Did everybody hear that? Question was, what happens when you have connections from a beam, I guess, to a column, where the connections are offset because of the OSHA bolt, the bolting safety rules, basically? I think the answer is that what you're talking about, I think, is a temporary condition, right? Because eventually there'll be a top slab. Okay, well then I think it becomes a matter of engineering judgment as to whether or not you think you have enough rotational restraint there. And one of the things you could do, and I can't think of any simple rules. I guess my rule would be if you provide the connection within 2/3 of the depth of the section, you have bolts, you're probably going to be okay. And it might even be as little as a half. But let's say 2/3 to a half, you probably have enough rotational restraint. If you're unsure, it's real simple to just model that beam with a finite element mesh on SAP and just see what it does. You'll find out whether or not you can reach the full moment capacity by just continuously applying the load and see if the thing twists. If it twists enough where you can't reach the full moment capacity, then you know you're not braced well enough. One of the things, I'll just tell a quick story about this kind of thing, is that and I'm sort of coming from the old generation now. I hate to say this, but I grew up with the slide rule, okay? And then there was calculators, wow. And now we got this enormous power at our desktops with these finite element programs. It's real simple to plug into an elastic finite element program and answer questions like that. Also to answer questions about is a beam braced here or isn't it? If you model the situation accurately in your computer program, you'll answer these kinds of questions. So don't hesitate to do it, because and maybe you don't want to do it if you're not the computer whiz in the office, and believe me, I'm not. But boy, I got some smart guys in the office that know how to set up these finite element programs and run these analysis in a matter of 5 or 10 minutes. You'll answer the question. So the answer is, I'm afraid there's no simple answer, but probably it's okay. But you may want to do the analysis to check it. Absolutely. I mean, as soon as you start taking away flange, you're going to be reducing the capacity of the section there and leave yourself more open to local twists there that might prevent you from reaching its full capacity. But again, your finite element model will probably tell you that. And of course, when in doubt, you can always stiffen the section. which I know is not popular, particularly with fabricators, but you know, unfortunately, you got to get the design done. If you don't have time to do a more sophisticated analysis, you take the simple way out and you strengthen up the section at that point. Any other questions? Yes, ma'am. Right. Yeah, if you were to load up just load up a section with a moment, when the section first yields, let's say that's 1 theta, okay, and then we're going to continue applying that moment till we get three times that. So it's 3 times the rotation you would get at first yield. Now, when you're in a seismic area, you may have to go way out on that low deformation curve, and 3 may not be enough. You may have to go to 5, a ductility factor of 5, if you will. So the low seismic and wind requirements in the table, in that B table in Chapter B, are not as severe as they are in the seismic, where they require bigger B over T or smaller B over T ratio so you can get higher rotational capacity. Think of it as a ductility factor. It's really what it is. Right. Yes, sir.
In some of these simple traditional lightweight slabs with deck and lightweight concrete, say a 2, 3.5 application on steel beams, a headed stud traditionally in my mind is a simple way I get real good continuous bracing of my top flange. I have had 3 applications now where contractors want to cut their costs and use puddle welding of the deck to that top flange and want to consider that and argue about that rigidifying that top flange. Is there a case where you can argue that a puddle weld is actually a top flange brace?
Everybody, I think, heard that one, right? We have the mic here. Most specifications, ours included, require welding patterns of metal deck to the beam, either a floor beam or a roof beam. And in our case, it depends on what wind zone you're in. If you're in a low wind zone, then we usually go to the Steel Deck Institute minimum requirements. But if you're in an I-60 or an I-90, one of those higher wind uplift classifications, then our specification requires more welding of the metal decks to the beam, and those are usually 5/8 inch puddle welds, and in some cases in high seismic zones they even use 3/4 inch puddle welds. And in my experience, those puddle welds are pretty good, and they would provide the necessary bracing to that compression flange. I really don't think you have to worry about that. Where you do have to worry, I think I'm going to talk about this in the composite section next, is when you have a girder and the metal deck, composite deck, is running parallel to the girder. In many cases, if you're making that girder composite, which you typically would, you want to put studs on the top flange of that girder, and you want to be sure that you're getting concrete coming down to the top flange with the stud on it. And in many cases, it means that you have to break the deck, and the contractor has to put a pan there, if you will, to ensure that he's getting concrete over the top of that, and so he can put the stud on there and make the girder composite. Now, there have been cases, and we got involved in one, where there's actually a girder failure during construction, and the engineer had assumed that that girder was fully braced along the full length of the span for the pre-composite situation, that is the wet weight of the concrete and construction loading. And it turned out that the girder flange twisted, and a bunch of workers actually fell, and somebody was killed, and therefore the big lawsuit. And what was found was that the pan, this is a situation where the metal deck guy put a pan there, and the contractor had just done a couple of tack welds of that pan to the top of the girder, and so really there was nothing There's nothing bracing that girder except the beams that were coming in at the third points. Well, this was a really long span, so that unbraced length was long enough where it didn't provide sufficient bracing capacity for that girder for the construction condition, and you actually had a lateral torsional buckling failure. So your question is a good one in the sense for girders, I would suggest you pay close attention to that. For cases where you have deck crossing the beam like you have with a typical composite beam, I don't think you're going to have to worry about that. If you put a puddle weld every 12 inches, which is probably what most specs would say, every 12 inches you attach that metal deck, maybe 36 inches depending on your spec. I forget what SDI is, but there is a minimum in the Steel Deck Institute spec about how you attach that. I think you're going to find that's sufficient bracing. One last question, and then.
Well, if you're equation B in many cases that exceeds the value of 3, in fact, example 3 appears to use that, but yet you said earlier AISC limits it to a value of 3.
Yeah, everybody heard that question. That C sub B. The question was what happens if you plug into the C sub B equation and you get a value larger than 3. Well, when we did the seminar, the 2005 spec wasn't out, and there was no limitation on C sub B. So that's one answer to your question. But if you really look at that example, we didn't need a C sub B, even though we calculated a C sub B value that was pretty high. We didn't need that high, and usually 3 is going to get you there. So I'm not sure why the spec committee, the guys that do Chapter F, why they put that limitation on there. There really isn't a very good explanation in the commentary that I saw. And I think it's just one of those things, there's probably no research to justify a value much higher than 3, so they just put that ceiling on there. But I think you're going to find from a practical standpoint, 3 is going to get you there most of the time. Okay, do we want to take a break, Steve? We want to keep going here? Okay. Okay, our next section here, we're going to talk about composite beam design. And when we were putting this section together, we knew we just didn't want to tell you how to design a composite beam, right? That's pretty boring. Most people aren't doing it by hand anymore anyway. They're using computer programs. So we said, well, let's talk about something here that's a little bit more practical. And unfortunately, composite beam construction is probably the most common thing that we do in the design of steel buildings. Everything's composite floors, right? It's probably the bread and butter, the staple of structural steel building design today. But boy, there's a lot of problems out there with utilization of composite floor construction. There are things like floor flatness, floor levelness, camber, studs, weak studs, strong studs. I mean, a whole myriad of issues that seem to come up and get us practicing engineers at odds with contractors and owners over the end product. So we try to concentrate on some of those practical problems, and as you might expect, there's no simple answers to a lot of these problems, but there are tips. We're going to talk about some of the tips you can use when you get into some of these problems. We listed 10 things we're going to talk about in this section, but the material considerations, steel and concrete strengths, for instance, the stud strengths and all that. Fire resistance issues, which are of course, something we have to face with the architect as engineers. Deck and slab considerations. We're going to talk about some strength and design issues. Camber, big issue. Serviceability considerations, deflections, vibrations. Design and detailing of the studs, and particularly the new stud capacities that have come out in the new 2005 spec. We're going to touch on that a little bit. What do you do about reactions in the design of the connections for composite beams? Composite beams in lateral load systems. I want to talk about that one because I think you'll find this one kind of interesting to get you some more drift capacity that you might not have otherwise known about. And then I think all of us have probably been involved in taking an existing floor and the owner says, hey, it's designed for 50 plus 20. I want to make it designed for 150. What do I do? Well, that's strengthening of existing composite beams. We're going to touch on that just a little bit. So that's what we're all about in this section. I think all of us generally have a pretty good understanding of what we're talking about here. A steel wide flanged beam with a composite metal deck, usually 1.5, 2, or 3 inches deep, that has embossments on it that make it a composite deck. That is, the deck itself serves as the reinforcement for the slab, in addition to being a form for the slab. And then shear connectors, usually 3/4 inch diameter, that make our beam, steel beam, composite with the slab. It's the bread and butter of structural steel building design. Here's an example of it. You can see the embossments on the deck that help make it composite. There are the 3/4 inch stud connectors. Sometimes 1 stud per flute, sometimes 2, and in heavy situations you might find as many as 3 studs per flute on there. Here's some of the things you don't like to see. Kind of shoddy welding of those studs to the top of the beam. And notice the ferrule here that goes around the stud. The AWS specification requires that ferrule be removed after welding, and so the guy is supposed to take a hammer and break it away and kick it away. So you might want to watch that during your inspection. But you know, obviously this welding isn't the greatest here, so that kind of makes you nervous, and you want to do that bend test, that hammer bend test, as specified in AWS, to be sure your studs have been welded properly. A lot of times you can get problems with calibrating those guns, particularly in the early morning hours. There's a lot of moisture on the deck. If the guy hasn't calibrated the gun properly, you can find that a lot of the studs just aren't being welded on there properly, and that's a potentially dangerous situation. Here's what it looks like in the textbooks. In this particular example, it really does look very clean. That's sort of the way it should look. So, some of the material considerations we're going to talk about here. Structural steel, I think all of us are aware now that A36 and A572 are sort of things of the past for rolled shapes. In structural steel, we now use the A992 specification with a yield strength of 50 KSI. Obviously, by AISC, you can use pipes or hollow structural sections or built-up plate girders or just about anything as beam sections. The shear studs are commonly specified as ASTM A108 with 60 KSI. 3/4 inch diameter is the staple stud size used. Really no reason to use 5/8 or 1/2. For buildings, 3/4 usually gets you what you need and is commonly stocked. Slab reinforcing steel, welded wire reinforcing is commonly used in the composite slab. Reinforcing bars can also be used. In our practice, we usually use mesh for commercial kind of office buildings, but if it's a institutional owner like a hospital and they're very interested in extra capacity in the slab or controlling cracking, we sometimes use a mesh of bars or a mat of bars. Some engineers also put steel fibers in the slab to help control cracking using ASTM C 1116. If you do that, be careful that those steel fibers have a UL rating, and so you want to check with your UL directory on that. One of the things that some engineers overlook is the fact that there's a requirement in AWS. It says that unless it's located over the web, unless the stud is located over the web, the diameter of the stud shall be less than or equal to 2.5 times the flange thickness. Now, a lot of engineers just sort of ignore that and say, well, the stud's supposed to be over the web and I'm not going to worry about that. Well, you might want to worry about it, because if you ever seen those guys in the field, they get going 90 miles an hour and they don't necessarily put that stud over the web because they really don't even know where the web is exactly. So in order to comply with that section, and assuming that they're not going to put the stud over the web, in our practice we don't use composite beam webs that are less than 0.3 inches in order to conform to this requirement. That means those sections listed shouldn't be used as composite beams if you subscribe to this line of thinking. And so that's, 10 by 12s, 10 by 15s, 8 by 13s, 12 by 16s, and so on. Those don't have a flange or a web thick enough, or a flange thick enough to conform to that requirement. So if they didn't have the stud over the web, it would mean that there's a potential for the stud ripping out and not developing its full shear capacity. Getting into the concrete, normal weight concrete, 3 KSI minimum, 10 KSI maximum. Lightweight concrete, 3 to 6 KSI. Higher strengths may be counted on for stiffness only, but not strength. Normal weight concrete normally is taken as 145 pounds per cubic foot, including the reinforcing. Sand lightweight or lightweight concrete. Be careful about the wet weight of your concrete, and because concretes around the country can vary considerably in their density, anywhere from 95 or 100 all the way up to 125 or even 130, depending on the aggregate they're using. So be careful when you're using metal deck catalogs, and be sure you understand in your location for your concrete what your density really is. One of the features of composite beam construction is that the deck slab generally cracks over the purlins or the girders. That's because we're designing the composite slab as a simple beam, and the concrete doesn't know it's a simple beam, so it tries to act like a continuous beam, and the concrete over the support there tries to take that negative moment. It can't. It exceeds the modulus of rupture, so it cracks. Those cracks have generally been shown to not affect the capacity of the composite beam or girder. Even though they might be big enough to stick a dime in, tests have shown that it really doesn't influence significantly the flexural capacity. But they can make an owner very unhappy, particularly if there's a tile floor or something other than carpet where those cracks might be exposed, or if it's a plain concrete floor. Most people aren't going to like that. So what do? Well, you probably should put either an additional layer of mesh in this negative moment region, or a lot of engineers like ourselves, we put bars actually chaired up over the support to try to control this cracking and keep it more as a hairline crack as opposed to a crack you can stick a dime into. And it's pretty hard to eliminate it altogether unless you really put some pretty good steel in there, because concrete, that's just the way it is, right? You get hairline cracks, shrinkage cracks, because contractors don't do as good a job as they perhaps should in curing, moist curing these slabs, and sometimes they're out in the hot, dry air, and that causes shrinkage and so on. The other thing, of course, is the deck serves as the positive reinforcing for the slab in the normal situation. And therefore, all we're putting in these slabs is minimum temperature and shrinkage reinforcing steel. Usually that's 6.6 W1.4 by W1.4 welded wire reinforcing. Does everybody understand the politically correct term now is welded wire reinforcing, not welded wire fabric or welded wire mesh? I guess the Welded Wire Institute people are becoming very sensitive to that. Or you can put 6.6 W2.1, which is a little heavier mesh in there. But it's basically shrinkage and temperature steel. Be advised that if you're using composite decks in parking garages or any situations where you can have a lot of dynamic loading, like areas where you have forklifts or vibrating equipment, you may not, and you probably should not, count on that composite slab as the reinforcement. That is, you probably should put bars in the bottom of the flutes that are counted on to take the moments. Because over time, if you've got a lot of vibration, the deck might work loose from the concrete, and you may not get that composite action that you counted on. And that's actually stated in most of the metal deck catalogs. Fire resistance is something that we engineers just have to be aware of. I think it's generally the purview of the architect to develop fire ratings, define the fire ratings required for the project, and then we help him out to pick the UL numbers that apply, to get the hourly rating that he wants. Depending on, you know, your architect and your area of practice, sometimes the architect thinks that's our responsibility and we're supposed to do all that. Well, what we try to do is help the guy out as much as we can, because most of them don't seem to know too much about the UL ratings for composite construction, so you end up being a consultant to the architect to help him solve those fire resistance issues. Normally you need 2 hours for floor beams and floor construction, 3 hours for the frame. And of course the UL directory has all these UL ratings in there that we want to refer to, or you want the architect to refer to. We're going to talk about some of the more common ones. But depending on the size of your project and the location of that project within the city or the county or wherever, you may not even need a fire rating. So you want to check that out and see. AISC has a nice design guide out, Design Guide 19, that was written by John Ruddy, which is a very excellent reference to aid you in designing steel structures for fire. Here's the UL directory that I think most of us are familiar with. There's 3 UL listings for composite construction that are the common ones that we reference, and I'm sure you do too. UL D916, D902, and D925 are the typical ones that address composite decks with shear studs and composite beams. Normally the strategy is to select the concrete thickness such that you don't have to spray fireproof the underside of the slab. You merely have to spray fireproof the beam. That's the norm, but in some seismic areas, I know on the West Coast, for instance, where mass becomes a big issue for them, and sometimes in their tall buildings, instead of doing 2 plus 3.5 lightweight to get a 2-hour rating without spraying the deck, they might cut that down to 2 plus 2.5 to save that extra inch of concrete or so. Multiplied over 40, 50, 60 floors, whatever, that can be a lot of mass savings. And in those situations, they would spray the underside of the deck, and they find out that that's the economical thing to do for that project. That's something that the engineer needs to look into for his particular application. But normally, we find that you don't spray the deck. You spray the beam, you put an inch and a 16th, inch and an 1/8 of fireproofing on the beam to get a 2-hour rating. The slab concrete is thick enough where you get the 2-hour rating automatically without spraying the underside of the deck. But just be aware of these UL ratings. Here's D902, which is another one. And here's D925. There could be more out there. Those are the 3 common ones that I'm aware of. Some of the important aspects of UL D916, which I think is the most common. The minimum beam size specified is 8 by 28. The normal weight concrete has to have a minimum concrete strength of 3,500 psi. Be careful there. Some engineers use 25 or 3,000. That may not conform. Does not conform to UL D916. For normal weight concrete, you normally have to have 4.5 inches of concrete over the top of the flute to get the 2-hour rating. For lightweight concrete, the minimum strength specified is 3,000 psi. The minimum concrete thickness is 3.5 inches over the top of the flute to get your 2-hour rating. And the listing requires 4 to 7% air entrainment in the concrete to match what was done in the test. These situations, as I said, the deck does not have to be sprayed. You normally put an inch and a 16th spray on fireproofing over the beam to get the 2-hour rating. Shear connectors are actually optional. They're not required. Most of the time you, of course, would use them. There is welding, going back to the gentleman's question earlier, there is a weld spacing at the supports requirement of 12 inches on center. Weld spacing for adjacent units, 36 on center along the side joints. So be aware of that. If you have a beam size different than the size that was tested, that is that minimum W8 by 28, you can still use it, but you may have to increase the thickness of the fireproofing in recognition of the thinner steel sections. And this equation that's in the UL directory explains that a little bit and how you would do that. Normally, as I say, this is in a specification, and it's not something that we structural engineers would put on the drawings necessarily, depending on your practice and your architect. This is a table that we put together for the common situations where you either have a 2-inch or 3-inch deck, and you either need a 2-hour or a 1-hour rating, normal weight or lightweight concrete. For each situation, we're giving you the concrete thickness there, and then we're giving you the stud, the 3/4 inch diameter stud length, minimum requirement, what both before welding and after welding, and then a recommended size or recommended length. Remember that the studs must be 1.5 inches above the metal deck flute. But I think you'll find this table kind of handy to just decide what concrete thicknesses you need with composite deck construction, depending on the hourly rating you're looking for. Here's another handy table we put together that just tells you for different deck sizes, what gauge deck you need. Normally, you don't want to shore these decks during construction. I think most contractors will tell you that it's cheaper to get a metal deck that's heavy enough to span the purlins such that you don't have to shore the deck. So depending on the gauge thickness, this table tells you for 2-span conditions, and we generally tell the contractor he has to use 2 or 3-span conditions. We don't let him design for simple spans, and there's actually several reasons for that, but usually the guy that details the deck can always get either a 2 or a 3-span condition if he lays it out properly. You generally don't want to use simple spans because it's a potential safety problem if you put a simple span deck like in an elevator lobby, spanning from elevator front to elevator front. We found that that's a safety issue, that the deck could slip off the support if it's not put on there exactly right, and therefore our high-rise erectors have told us, please don't use simple span decks. So we usually turn the deck around and run it parallel to the front of the elevator, so it's always a 2 or a 3-span condition. So our specifications always say 2-span minimum. And of course, it's more economical too to do a 2-span than it is a simple span. So one of the gotchas in composite beam construction involves concrete ponding. Like it or not, when you're spanning a 2-inch deck or a 3-inch deck, 9 to 12 feet, the metal deck is going to deflect. At mid-span, you might get as much as a 5/8 or a 3/4 inch deflection, and if you calculate that extra concrete over 1 million square feet of floor in a building, that ends up to be a little piece of change for the contractor. And we learned the hard way that you want to put in your specifications that concrete that's required because of ponding and deflection of the deck is the responsibility of the contractor to include that in his bid, and that it does exist. Otherwise, you might get a RFI with a change order request that says, hey, I had to use more concrete here because it wasn't 2 + 3 1/4, it actually was more than that. So just be on the lookout for that. I don't know if any of you ever had that problem, but we had it once, and so now our specification makes it very clear that the contractor is responsible for the extra concrete because of ponding. Consider the wet weight of lightweight concrete. As I mentioned earlier, you can get all kinds of lightweight concrete depending on the aggregates in the local area you are that can weigh anywhere from 115 all the way up to 130. And the UL listing does have a limit on that. And so be sure you don't get caught with a concrete that doesn't meet the UL requirements on density. That can be a very painful problem to solve. Be aware of vendor catalogs that oftentimes talk about setting up their load tables with 110 pound per cubic foot concrete. Well, we don't often see 110 pound lightweight concrete. It's usually 115 or more. And so be careful you're not using catalogs that say 110 when you really have 115. You may have to adjust the loadings because of that effect. This slide just talks about the design of composite decks and beams. One of the issues that comes up quite frequently is what is the minimum composite action you want to design for? And in our practice, we don't like to go as low as 25%. There is no limit, by the way. Many engineers use 25%. I try to keep it a little higher than that, actually, because when you get down to 25% composite action, you are really working those studs very hard. And as you'll see in a little while here, you're really straining those studs significantly up to a high strain, and therefore you're running the potential of breaking them if they haven't been welded on properly. Yes.
Why don't you continue with the strength design topic after our break? Let's take
Okay. We are, yes, we're close to 10 o'clock here now, or 10 to 10, so we're going to mark your place here. We'll come back and then let you get up and stretch your legs and get a drink of water.